Hello again, everybody. It's Cal here from Wise Guys Tutoring. I apologize in advance that I sound so nasal. It's just that I got a pretty bad cold. But anyway, today we're going to continue with the EmSAT Math Specimen 2020 paper. Today we'll do questions 21 to 25. And as usual, I'll try to give you some background on the topic of each question so that you have a better understanding overall. So without further ado, let's do number 21. So this one says, which sketch shows the inverse of the equation given below? And the equation is y equals a to the x with a greater than 1. So there's a lot to unpack here. First of all, this is a exponential function. The standard form is y equals e to the x. Okay, but the base, which is what we have here, can be absolutely anything. And the exponent has to be some function of x. In this case, we don't have e to the x, we have a to the x, a being some number greater than 1. And for our example, I've chosen 2. Let's keep it simple, right? And I've obviously shown the graph here of 2 to the x. So let's see what happens with this function. How do you get this curve? And then we'll talk about its inverse, okay? So first things first, when x is equal to 0, that means 2 to the 0. And this is a very known rule in exponents. Anything to the power of 0 equals 1, no matter what it is, okay? 1,347,000 to the power of 0 is 1. And minus 5,984 to the power of 0 is also 1. You don't have to sweat it. Anything to the power of 0 is 1. Well, except 0. 0 to the 0 would be 0. But anyway. So that's how they got the first point here. When x is 0, y is equal to 1. Now what happens when x is 1? Well, 2 to the 1 is just 2. And that's how they got this point 1, 2. And 2 to the 2 is 4. That's how they got 2, 4. And 2 to the 3 equals 8. And 2 to the 4 will be 16. And what you notice here is that this y value is growing really quickly. It's not growing linearly. It's not growing by 1 every time. It's not growing by 2 every time. It's grown first by 1. And then it's 2 more, then it's 4 more, and then it's 8 more. So as you can see, it's increasing by more and more at each step, okay? And I'd like to take this chance to just compare it to another function. Let's use a different color. Let's say it's y equals 2 times x, right? This one, when x is 0, 2 times 0, that's 0. And when x is 1, you'll get 2 times 1 is 2. And when x is 2, you get 2 times 2 is 4. And 3 you get 2 times 3 is 6, and 4 you get 8. And let's compare these values. You see how different it is, right? This one's going up by 2 every single time, and by the time x is 4, it's only at 8, whereas this one's already gone to 16. This one here will, it will grow much faster. Okay, when the base a is bigger than 1, then it will expand extremely fast on this side. But let's see what's happening on the left side. So on the left side, what's happening is x is negative, right? So if we, let's continue our board for the negative values. Let's say I have 2 to the minus 1. When you have a negative exponent, what that means is you're supposed to invert your number here, your base. So if you're not sure, I can assure you that the denominator of a whole is like 1. You just don't really see it. It's like 2 over 1. So 2 over 1 to the minus 1 is 1 over 2 to the power of 1, which is just 1 over 2. And that's why you get a smaller value when x is negative. Let's see what happens when it's minus 2. You invert it, so that's 1 over 2 squared, which is 1 over 4. 2 to the minus 3. I think that's the last one. I think you guys get the point. You invert it and you keep the exponent, so you get 1 to the 8th. So in fact, the more negative x is, the smaller your value of y. So that's why it takes on this shape here. Okay. One thing to be said is, it says here the x-axis is an asymptote. Now an asymptote just means it's a line. It's a line that my curve will never touch. Will never cross nor touch. But it will get infinitely close. Okay, the reason it will never touch it is if you look at this equation, if you look at y equals 2 to the power of x, there is no value of x, none, that will make this equal to 0. 2 to the power of 0 is 1, and 2 to the power of a negative number is some fraction, but it's never 0. It can get extremely close to 0, but it will never actually touch 0. That's why you get this asymptote as the x-axis. That means my curve will go infinitely close to x as it goes towards the left, but it will never really touch it. Okay, so that's the exponential function here. It should be noted though, if a, they mentioned that a is bigger than 1. Why did they say that? It's because if you got a smaller than 1, so if a was a fraction, let's say this was like 1/2 to the power of x, right? What would happen? So when x is 0, remember anything to the 0 is equal to 1. And when x would be -1, remember that means flip it and keep the exponent, so you end up getting 2 to the power of 1, which is just 2. And then you'd get to the power of -2, remember you flip it and you keep the exponent, it becomes 4, and so on. So what we can see here is that on the negative side, it's actually growing quite fast. And the flip side of that is 1/2 to the 2, it's a small number. It gets smaller, right? Because half times half means half of a half. That's even smaller than a half. And if you cube it, that means half times half times half. That's even smaller than a quarter. And that's why if a, here we go, if a is smaller than 1, then what you'll actually get is a very high numbers on that left side, right? You'll get higher numbers here, and you get the low numbers over here. See? You'll get lower and lower and lower. So it would actually look like this if it was a less than 1. If your base is less than 1, that's what it would look like. Okay, you would get the opposite effect. Alas, now let us answer the actual question, right? So it says, which one shows the inverse of the equation given below? So as long as a is bigger than 1, then we should get rid of this purple one. And let's focus on our original one. So when you have an inverse, the easiest way to see it, visually, is to draw a line of symmetry. So maybe I'll make a red line here. It's basically the line that passes by, x is y. Which passes by 1, 1, 2, 2, 3, 3, right? And this is going to be like a mirror line for us. Okay, this is like the mirror. And you just need to take the reflection of your function. So why don't I do it in green? Because I'm running out of colors here, people. So this point will be one of them, right? And then where else? You got 2 and 1, which is here. And you got 4 and 2. So I'm just inverting, right? I'm inverting these. So this point is 4 and 2. And this point here is 2 and 1. And this point here is 1 and 0. So I'm just flipping the coordinates, basically. And what you end up with is a curve like this. And if you look over here, you will notice that it is A. Right, the most telling point is this one, and again, if you use the mirror image, then you get this kind of curve. Okay, let's move on to 22. Question 22 says, what is the length of side AC? And they give us some clues here. They say AC is parallel to DE, so here's AC and here's DE. They say AD is 24. And they say DB is 12 and DE is 4. So, there's a lot going on. First things first, I can already tell that this is going to be a problem about similar triangles. So we should probably talk about that. When you have similar triangles, what that means is they have all 3 angles the same. And when they have all 3 angles the same, that means that they will have proportional sides. All their sides will be proportional. Let me show you what that means. So here I've drawn the 2 triangles. Let's say this is triangle ACB, the big one, and this one would be triangle DE, and it also shares point B, right? So all I've done is I've sort of split, this is the little one and that's the big one, So I've just kind of split them apart so we can see them a little bit better. So let's put some of this information down. So we know that AD is 24. Well, AD, I can only put it over here. So this is 24. DB is 12. So this part here is 12. Well, what this tells me is that AB is 36. So here it is. And DB is 12. So why don't I put it over here? We also know that DE is 4. Here it is. Okay. So first, before we can do any ratio thing that I was talking about, we first have to prove that these are in fact similar triangles. So do they have all three angles the same? Let's start with this one. This one is clearly the same because it's the same point, right? It's the same corner of the same triangle. Both of them will have the same corner here, right? But what about for, the angle at A and C and D and E? So this is about the parallel lines and a transversal. So let's assume these two lines here are parallel lines, and a transversal is just a line that crosses both of them. So let's say something like that. When this happens, if the two lines are parallel, then what we get is some corresponding angles which will be equal. So corresponding means this angle is equal to that one, and this pink guy is equal to this pink guy. So it's like, same seats sort of situation. Where you are at the intersection, they will be equal. So like this guy here will be equal to this bottom right one, and this here left one will be equal to this left one. That's why they mentioned that AC and DE are parallel, right? So if this side is parallel to this side, well then I get these corresponding angles as well. So this angle will be the same as this angle because they are corresponding. You also have these angles on top, which will be equal. This one here and this one. Again, for the same reason, you have two parallel lines and a transversal. So if you're at the bottom right of the intersection, these two will be equal. These two are like at the top right corner of the intersection, and they will be equal. So that way we've proven that this one and this one are equal, and so is this one and this one. And therefore, we can confidently now say that triangle ABC is similar to triangle DBE. Now the order of the letters matters here, okay? Because what these are corresponding points. So A is like the brother of D, you see? And B is obviously the brother of B here. And C is like the brother of E. And that's how it works with similar triangles. What it means is that the ratios of the line AC, the length of line AC divided by DE will be equal to AB divided by, so AB divided by DB, right? They will have the same proportion. And also CB will be the big brother of EB, okay? So whatever the values of AC and DE are, okay, when I divide them, I'll get the same as EB divided by DB. Why is that? Because these are like, brothers, okay? AC is like the brother of DE. You see that? And AB is like the big brother of DB. And then you got maybe purple, there you go. CB, sorry, is the big brother of EB. So whenever you do these ratios, whenever you compare them, then you will get the exact same value. And this is great for me because it helps me figure out all the rest as long as I have one pair. Now the question is, do we have any one pair of brothers here? Yes, we do. We have this one, right? We have AB and DB. We have this one, right? And I know that it is equal to 36 over 12. Which means all of them will be equal to 36 divided by 12, which is 3. So if they're asking me, what is the length of AC, right? So I'm looking at this one. And I know that that ratio is equal to 3. So I'll say AC over DE is equal to 3. Now I know what DE is. They gave it to me. It's 4. So I'll say AC over 4 equals 3. And if you can do a little bit of algebra, you multiply both sides by 4 to get rid of this denominator. And I'll get my answer that AC is equal to 12. Meaning the answer, as usual, A. So that's similar triangles, right? So as long as you can prove that 3 angles are equal, then you can bust this ratio here. And as long as you have one of these pairs, then you can pretty much find whatever you want. Okay? Let's move on to 23. So Aisha calculated the area of a piece of paper to be 50.27 centimeters squared. The actual area of the paper is 55.42 centimeters squared. So quite a way off, right? Anyway, what is the margin of error in calculating the area? When we're doing error, this is how you calculate it, okay? So the error is what we call accepted value minus experimental value. Sorry about my handwriting. It's, I write in cursive because I studied in French. And you divide that by accepted value. So what do these mean, right? Accepted value can be thought of like the true or actual, actual known value. That's what accepted value represents, right? So it's the accurate, the correct one, the real one, okay? When we talk about experimental, this is sometimes called the measured value. So it's the one that you measured when you were doing your experiment, okay? And these lines over here, these are absolute value lines. That means whatever the difference is in here, whether it's positive or negative, we're gonna make it positive, right? So if it's positive, you take it positive. If it's negative, you take it positive anyway. That's what these two bars mean. This is called absolute value. Okay, so that will be the error. Sometimes they like to get the error in percentage because this will give you a decimal. Sometimes you want a percentage, so you would just multiply it by 100. In our case here, they do not want percentage. They just want the actual margin. So they just want the decimal number. So we can get rid of that. So let's go on and calculate. Now, which one is the true or actual value? Well, actual area is 55.42. I'll put my bars here. Experimental value, so that's what she calculated. That's what she measured, right? It was 50.27. There you go. You divide that by the accepted or, the true actual value. And this should be our answer. So the top will be positive anyway. You put that in your calculator and you get 0.9292926, etc., etc. Right? So they want you to round off to that thousands. So to round off over here, I just have to look at his neighbor. If his neighbor is 5 or more, then this 2 gets pushed up to a 3 and everybody else disappears. So his neighbor is a 9 that is bigger, equal or bigger to 5. So this 2 becomes a 3 and everybody else goes away. So your answer is, as usual, A. Let's do number 24. So here it says, how are these figures related? And we have the option of all these transformations and not related, right? So let's go through a process of elimination here. So what I see in front of me is these two shapes are actually the same size, right? There's not one bigger than the other. So this side here is 2 units, for example, and so is that side, etc. So dilation will be ruled out, okay? Not related, I mean, it's possible, but when I look at them, I can see that there's some kind of relation. I'm going to leave it there for now. Now, translation means that this shape would have been slid somewhere, right? It would have been shifted. And the thing about translation is the size does not change, neither does the orientation. In this case, the orientation has changed, right? So what I mean by that is if I had this triangle and I wanted to translate it, then the image would have the exact same orientation, right? All the points will be in the same position relative to each other. They wouldn't be flipped over like this, for example. So that's how I know that translation will also be out. Next is rotation, and rotation is when you're turning your shape, right? It will not change size, but it will be turned. And if I take this and I turn it, by 90 degrees, it would look like this. And if I turned it another 90 degrees to 180, it would actually look like this. And that is not what we have. So that's how I know that rotation will also be out. Okay, how did I figure this out? It's because, you see, if you have a vertical side like this and you rotate by 90 degrees, this vertical side would actually become horizontal, right? So it would take on this kind of shape. And if I did another 90 degrees to 180, that means this same horizontal side will become vertical again. But in this case, the shape would look like this. And that is not what we have. So it is not rotation. Okay, and the last thing would be to check the reflection, which, to me, it looks pretty apparent that this kind of a mirror in between these and this shape got reflected. It got kind of flipped over across that line. The question would be now, how do I find that reflection line just to make sure? Well, this is how you do it. If this point is over here, right, at x is 1, and I count off to his brother over here, so that's 1, 2, 3, 4, 5, 6 units away. And if I take this point over here, let me see, it is at 3, and that means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units away. So when you're doing that, that's how you find the mirror. The mirror should be exactly in between the points, and it should be in between each pair of points. So if we said the distance here was 6 between these two, that means the mirror should be 3 away from each. So if I was to trace that mirror line, it would be over here at x is minus 2. Now let's see, does that work for the other points, right? I had another pair here, 1, 2, 3, 4, 5 away from the mirror, and 1, 2, 3, 4, 5 away from the mirror. It'll work for all of these, right? Because they are aligned. So yes, it is a reflection about the x equals minus 2 line, but they don't ask that. All they want to know is that it is a reflection. So your answer is A. So let's do number 25. So for 25, we have a simplification of this algebraic fraction. So let's go through this. Now I can see that my denominator has x squared minus y squared. And this is called a difference of squares, or difference of two squares. And it's actually easily factorizable. So when you have a difference of two squares, that means you have a perfect square minus another perfect square. All you have to do is open two brackets, right? You put the square root of this one here, the square root of that second one here, and what you have is x plus y times x minus y. Now, the reason why this works is, let's foil it, right? Let's develop this, let's expand those brackets, and let's see what we get. So the first term is x squared, then you get minus xy, then you get plus xy, and then you get minus y squared. So you'll notice that these two middle terms will cancel out. And this will always happen when you set it up in that way, when you have, a plus b times a minus b. When you have this difference of squares and you factor it this way, you will always end up eliminating those middle terms and getting this one squared minus that one squared. So that's how you factorize the bottom. So let's simplify it right off the bat. So we have it now equal to y minus x over x plus y times x minus y. Now the problem is I still don't see anything I can cancel, but this y minus x and x minus y, I mean, they're very similar. So I'm going to play with the top here. I'm going to put a minus in front of it, and I'm going to change the order, right? Because once I've done this, what it means, it's as if there's a 1 here, right? Like minus 1. So if I expand this bracket, what I get is negative x plus y, which is the same thing as this, right? Negative x plus y. So by adding a minus, I was able to kind of flip the order of them and have it this way. And now I notice that I have a similar term there on top and on bottom, which is x minus y. Remember, when you have a term on top, so if you're multiplying by something and dividing by that thing, we can always eliminate them because they undo each other. They equal to 1. And so this is equal to minus 1 over x plus y, meaning that our answer is A. Okay, so it was just a matter of kind of knowing the difference of squares property that lets you factorize them in this way. And secondly was how to get 1 or -1. You just kind of had to reverse the order here. If it had been x minus y, then we could have just canceled them out and left with 1. But because they are y minus x, I had to put that minus in order to flip the order. Now I can cancel them, but what I'm left with is not 1, it's -1. And that's how you get your answer. So that's it. That's question 21 to 25. I noticed that question 1 took a super long time compared to the others. The others were, simpler concepts, or more straightforward at least. Anyway, I'm going to do another video for 26 to 30 as soon as I can. As usual, if you have any comments, suggestions, questions even, just leave them in the comments, and I'll get back to you as soon as I can. Please make sure to like the video and subscribe, and I'll see you guys soon. Thank you.